Hi everyone. Today we're talking about IFIT. IFIT is an in-band flow measurement and O&M technology. It measures the quality of service flows by inserting IFIT headers into real service packets. Measurement data can be reported in real time through telemetry. IFIT lays a solid foundation for intelligent O&M, as it enables you to guarantee SLAs and achieve far more effective network O&M and performance monitoring. IFIT is mainly classified as application-level measurement, which measures the quality of service flows, or tunnel-level measurement, which measures the quality of forwarding paths. Today, we'll look at how to configure tunnel-level IFIT. EVPN L3 VPN v4 over SRv6 TE flow group networking is used as an example here. Such networking implements intelligent traffic steering by collecting packet loss and delay statistics of each candidate path using IFIT and diverting traffic to SRv6 TE policies through TE class values. This allows forwarding paths to be quickly adjusted if their quality deteriorates. Before configuring IFIT, you need to configure EVPN L3 VPN v4 over SRv6 TE flow group and ensure that it is running properly. For details, see Deep Dive into EVPN L3 VPN v4 over SRv6 TE flow group. The configuration roadmap is as follows. To begin, configure a clock protocol so that devices can synchronize their clocks. We use NTP as an example. Next, configure IFIT for SRv6 TE policy and create an IFIT instance on each PE. This ensures that statistics on the packet loss rate and transmission delay of the forwarding path can be periodically collected. Finally, configure PE1 to send measurement data to the NMS through telemetry. Let's dive into the specifics. Accurately measuring indicators such as the packet loss and delay relies on devices having synchronized clocks. Here, we'll use the forwarding path PE1, P1, PE2, and NTP as an example. Configure PE1 to use its local clock as a Stratum 2 NTP master clock. A smaller stratum value indicates higher clock accuracy. In addition, specify interface 1-0-0 as a listening interface. In this case, PE1 can receive NTP packets from only this interface. On P1, you need to specify PE1 as its NTP server, and specify interface 2-0-0 as a listening interface. On PE2, you need to specify P1 as its symmetric passive peer to implement clock synchronization between the two devices. Although we could use other protocols to implement clock synchronization, using NTP is recommended because the tunnel-level IFIT application scenario often involves interworking between Huawei and non-Huawei devices. Moving on, we need to configure IFIT in the SRv6 TE policy view to measure the quality of available candidate paths. Specifically, 1. Enable packet loss measurement and delay measurement on the PEs at both ends. 2. Configure an IFIT measurement interval. We use 10 seconds as an example, but different network conditions and device performance specifications will determine the value you use. Here, we use end-to-end measurement as an example. If you want to use hop-by-hop measurement, you need to run the IFIT measure mode trace command. After configuring IFIT for SRv6 TE policy, we need to create an IFIT instance on each PE. Specifically, 1. Enable IFIT globally and configure a globally unique NE-ID on each PE. 2. Configure an IFIT working mode. Here, we configure PE1 as the measurement control point, MCP, and PE2 as the data collecting point, DCP. 3. Set the service type for IFIT measurement to SRv6 TE policy. After completing the configuration, you can run the display IFIT SRv6 segment list command on each device to check tunnel-level IFIT measurement configurations. The command output on PE1 is used as an example. It shows the flow type, measurement indicators, measurement interval, and policy attributes. We can use this information to verify whether the configurations are correct. You can also run the display IFIT statistic type command to view the collected packet loss and delay information. Now, let's look at how an IFIT header is encapsulated by parsing real service packets. The encapsulation format in tunnel-level IFIT scenarios is similar to that in application-level IFIT scenarios. FII identifies the beginning of an IFIT header and defines its overall length. The type value is fixed at 130, and the IFIT header length is 22 bytes. FIH uses the flow ID field to uniquely identify a service flow. The L and D fields in the FIH respectively provide the packet loss and delay measurement capabilities based on alternating coloring. Here, both fields are set. FIEH identifies the measurement mode, type, interval, and other important data. The value 1 indicates the end-to-end mode and the tunnel-level type of measurement, and the measurement interval is set to 10 seconds. Next, we need to configure PE1 to send measurement data to the NMS through telemetry. In the telemetry view, we need to 1. Configure the data to be sampled. This involves creating a sensor group and adding sampling paths related to IFIT measurement to the sensor group. 2. Configure a destination collector. Specifically, create a destination group for the sampling paths. Then, based on the collector type, configure an IP address and port number for the destination collector, and configure a protocol and encryption mode for sending data to the destination collector. 3. Create a subscription and associate the destination group with the sensor group. After completing the configuration, run the display telemetry subscription command on each device to check the telemetry configuration. Take PE1 as an example. You can view various pieces of information, including the source address, destination address, transmission protocol, and port number. At this point, we have completed all configurations needed to implement tunnel-level IFIT measurement. Let's summarize the service process of tunnel-level IFIT measurement. 1. After we enable IFIT packet loss measurement and delay measurement in the SRv6 TE policy view, the SR policy component instructs the IFIT component to create an IFIT instance when creating a segment list. The instance carries the segment list, measurement parameters, and peer IPv6 address. 2. The IFIT component assigns a flow ID to the IFIT flow carried over the segment list, creates an IFIT instance, and returns the creation result. The IFIT header is added to service packets to be measured on the ingress, and is removed on the inbound interface of the egress. 3. After receiving feedback indicating that the IFIT instance was created successfully, the SR policy component starts to subscribe to measurement data from the IFIT component by sending a subscription request carrying specified thresholds. The DCP collects measurement data from the forwarding module and sends the data to the MCP, which then summarizes the data and calculates the indicators. 4. If the IFIT component determines that a threshold is exceeded, the ingress advertises the measurement result to the SR policy component. 5. Finally, the SPR module of the SR policy component implements intelligent traffic steering based on the IFIT measurement result. For details, see Deep Dive into EVPN L3 VPN v4 over SRv6 TE Flow Group. That's all for today. Thank you for watching.